KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.com.
In continuation to the last class, in this class we are going to discuss the topic acceleration due to gravity of earth. Okay ma? Right. So this topic is very important for us because in this topic or with this topic we are going to derive an important formula, that is small g is equal to capital G into capital M E divided by R E square. That is the conclusion what we are going to get from this class. Okay, right. See here, you know, when we are going to see the earth, when we are going to see the earth, you know, every body is going to pull by the earth with certain amount of force. That force generally we call it as gravitational force. But the thing is, when we are going to experience that force, not only ourselves, any body of certain mass, when it is going to experience that gravitational force by the earth, for example, you take earth. When any body of certain mass is going to experience some gravitational force by the earth, there itself, if you want to calculate acceleration of the body, acceleration experienced by the body due to the gravitational force by the earth, there, you know, acceleration is equal to, A is equal to small a is equal to capital F by small m. That is what from Newton's second law of motion, acceleration A is equal to capital F by m. So that is what the ratio of force to mass. But here force means that is the gravitational force experienced by the body due to the earth. Then mass means that is the mass of the body. Suppose for example yourself, you are falling from certain first floor, or when you are jumping from a certain height of that is what from a tree to the earth or ground, right? So there itself you are also like a freely falling body, and there itself to calculate the acceleration developed within you, we have to take the mass of yours, right? That is what generally 60 kg or 40 kg or 70 kg depends upon the person, right? So what I am saying is, in this entire universe, Earth is one of the planets. So that is the living planets. So where we are living, right? So due to the Earth, if we need to calculate the acceleration produced or developed in a body of certain mass by the earth, we need gravitational force. That's what we already calculated, and we can calculate by using the formula F is equal to G mm by R square, right? G is the universal gravitational constant and m is the mass of the earth, and here if you take earth as one of the object, m is the mass of the earth and small m is the mass of the body, and capital R is the distance between the object and the earth. Small r or capital R, whatever it may be, usual notation, that is the distance between the center of mass of the body and center of mass of the earth. Okay, right. And now you see here, I will explain you sentence by sentence what they have given in our textbook. See here, the earth can be imagined to be a sphere made of a large number of concentric spherical shells, with the smallest one at its center and the largest one at its surface. Right? See here, ma. The earth can be imagined to be a sphere made of large number of concentric spherical shells with the smallest one at its center and the largest one at its surface. And the largest one at its surface, right? I hope you are able to imagine. Imagination is very important and compulsory. Imagination is romba mukyama, right? In physics point of view, right? So earth means it is what? Spherical shell, right? It is in the shape of sphere, no? Okay. So when it is in the shape of sphere, you just imagine the earth in terms of concentric spherical shells, right? What is a sphere? You know, from geometrical mathematics. You just imagine a small sphere and big sphere. The radius will be different, no? Okay. So that's why here, ma. So to understand this sentence, this three lines of information, we have to imagine Earth's in different parts. I mean, different parts means yes, every part is producing again a sphere, again a sphere only, okay, not other shape. So that's why, see here, the earth can be imagined to be a sphere made of a large number of concentric spherical shells with the smallest one at the center and the largest one at its surface. Full stop. A point outside the earth is obviously outside all the shells. A point a point outside the earth is obviously outside all the cells. Is it okay? Are you agreeing with the sentence? See here. For example, it is the earth, ma. It is the point. So this is what? A point outside the earth, no. So when you take point outside the earth, that is, that point is obviously outside all the cells. Am I right or not? Outside all the cells. Full stop. Thus, all the cells exert a gravitational force. Thus, all the cells exert a gravitational force at the point outside, just as if their masses are concentrated at their common center. For example, it is the earth, ma. You can see this picture. See here, it is the earth surface, right? So I have written clearly here, and it is right. So that is also is one of the concentric sphere, concentric spherical shell, and this is another concentric spherical shell, and it is another concentric spherical shell. Don't think that earth is in the form of circle, because on the board I drew like that, but actually it is a sphere, no. So it is like it is one of the sphere, and it is also one of the sphere. Okay, right? And it is what the small r, and it is what the capital R E, and it is the distance between these two concentric cells, and it is the point P, and it is the mass of this particular object, and whatever it may be, but mass. Okay, because you can take you as an example, you can take a stone as an example, you can take some other as an example. So right, so mass means mass of that particular body or object or a human being, whatever it may be. And this is what mr, and it is what this I already told you, distance between the two spherical shells, right? It is completely the radius of the earth, ma. Completely radius of the earth. Okay, right. Now what I am saying is here, a point outside the earth, see here, ma, a point outside the earth is obviously outside all the shells, right? All the concentric spherical shells. I request you to imagine this point, ma. Now, thus all the shells exert a gravitational force at the point outside, just as if their masses are concentrated at their common center. At their common center. Okay, right. See, what is the common center, ma? This is the common center, no? This is the common center for all the concentric spherical cells. For all the concentric spherical cells. Okay, right. Now, see here, according to the result stated in section 8.3, right, that's what we discussed previously, and there itself we had a formula, that is F is equal to capital G into M1 M2 by R square, right? That's what we got in the section 8.3, and according to the result stated in section 8.3, the total mass of all the shells combined is just the mass of the earth. The total mass of all the shells combined is just the mass of the earth, right? That's what you are able to imagine, I think, right? Because, for example, it has certain amount of mass, ma, and it has certain amount of mass, right? When you are taking this spherical shell, from this spherical shell, you are taking only this part of the mass. And when you are taking this particular spherical shell, suppose you don't have any other shell inside, and then this is the mass, that is the mass of this particular spherical shell. Like that, if you combine the mass of all the concentric spherical shells, then it will give you the mass of the earth. That only he is saying here. The total mass of all the shells combined is just the mass of the earth. Is just the mass of earth, right? Full stop. Hence, at a point outside the earth, hence, at a point outside the earth, the gravitational force is just as if its entire mass of the earth is concentrated at its center. So, how the earth behaves while calculating the gravitational force by taking earth as one of the object, earth as one of the object or one of the mass, there we are imagining and we are taking and we are considering that the gravitational force is just as if its entire mass of the earth is concentrated at its center. Okay, right. Next, see this one. For a point inside the earth, for a point inside the earth, the situation is different. For a point inside the earth, the situation is different. See here, so this is what I already explained you this picture, and now what I am saying is, consider the earth to be made up of concentric spherical shells as before, right? Again he is asking to consider, ma. So whatever the imagination we had, that only he is asking to get back once again. So again consider the earth to be made up of a concentric shells as before, and a point mass small m situated at a distance small r, from the center, full stop. The point P lies outside the sphere of radius r, right? This is what one of the concentric spherical shell, ma. So the radius of this particular concentric spherical shell is small r. Here we are assuming a point. That point is outside, no? See this. That is what as before, and a point mass m is situated at a distance small r from the center of the point P lies outside the sphere of radius r, right? So this is the point. Actually it is like on the surface of it, but you just imagine which is on the surface of the earth, right? That is like outside. While drawing it is just like appearing like that, no? But you just take it as this is the point outside, right? Now for the shells of radius greater than small r, for the shells of radius greater than small r, here for the shells of radius greater than small r, the point P lies inside. So for this spherical shell, this point is inside, no? For this it is like outside, but for this it is inside. Okay, that's what he is saying. For the shells of radius greater than r, the point P lies inside. Full stop. Hence, according to the result stated in the last section, they exert no gravitational force on mass m kept at P, right? Full stop. The shells with radius okay, less than or equal to r, make up a sphere of radius small r, for which the point P lies on the surface. Full stop. This small sphere therefore exerts a force on a mass small m at P as if its mass mr is concentrated at the center. So as we discussed here, right? See, as we discussed here, the total mass of all the cells combined is just as the mass of the earth. Hence, at a point outside, the gravitational force is just as if its entire mass of the earth is concentrated at its center. Similarly here, when we are going to take this concentric spherical shell of earth, right? So when you are taking this one as a part, and when you are getting the discussion about this particular thing only, here also the same thing will repeat. That only he is saying here. That is, the small sphere therefore exerts a force on a mass small m at P as if its mass mr is concentrated at the center. Is concentrated at the center. Okay, right now. Thus, force on mass m. Thus, force on mass m at P has a magnitude. So, what is the magnitude? By using that formula, F is equal to G into M1 M2 by R square. G into M1 M2 by R square. So, what is that? F is equal to capital G into small m. Next, that is into mr, that is the mass of this particular concentric spherical shell of earth, divided by r square. This is the distance between these two, no? That's why that is what? R square. Now, see here, we assume that the mass of the earth, we assume that the entire earth is of uniform density. Uniform density. What is the density? Obviously, mass density. What is the formula, ma? Mass density means it is actually density. Here, density means it's the ratio of mass to volume. Density is equal to mass by volume. So, earth is in spherical shape. Earth is in the shape of sphere means what is the formula for volume of sphere? 4 by 3 pi r cubed, right? And what is the mass of the earth? So, if you take the ratio of mass to the volume, we are getting density. But here the discussion is we are talking about uniform density. So, the mass of the earth distributed uniformly throughout the sphere, throughout its volume. That is the point here. So, we assume that the entire earth is of uniform density and hence its mass is capital MA is equal to 4 by 3 pi r cubed into rho. You know that, just now I told you. Density is equal to mass by volume. Density is equal to mass by volume. Then mass is equal to density into volume, no? Mass is equal to density into volume. So, here that only is writing ME is equal to ME is equal to 4 by 3 pi into RE cubed into rho. Okay, right. Where what is ME? What is this ME, Amma? Where ME is the mass of the earth and RE is the radius of the earth and rho is the density, right? ME is the mass of the earth and RE is the radius of the earth and rho is the density of the earth. Terminology is very important. Okay. On the other hand, the mass of the sphere mr of radius small r is 4 by 3 pi rho r cubed. So, again here he is talking about this particular. On the other hand, the mass of the sphere mr of radius small r is 4 by 3 pi rho r cubed and hence F is equal to capital G into small m into 4 by 3 pi rho. 4 by 3 pi rho r cubed by r square. R cubed by r square. Now, see this, that is, I hope you understood here. In place of another m like this. So, in place of that he has written this one, 4 by 3 pi rho r cubed mathematically, right? This is the part of mr. And r square is the common term from this formula. Not only this formula, general formula you take F is equal to G into mm by r square. That is what we got from section 8.3. Okay, right. That is equal to Gm into me by re cubed into r cubed by r square. Right, r cubed by r square means obviously mathematically we are getting small r, no? Right. So, capital F is equal to capital G into small m into me by re cubed into r, right? This is what the expression we are getting here. Afterwards, I am telling one small point, that is what I already written here, but I am saying if the mass m is situated on the surface of the earth, if mass m is situated on the surface of the earth, then what about small r? When mass is situated on the surface of the earth, then what about small r? Small r is equal to Re, no? Small r is equal to capital Re and the gravitational force on it is F is equal to Mathematically, in place of small r, you just put capital RE. Right? It is RE cubed, it is RE. It will get cancelled and here RE square will come now. So capital F is equal to capital G into ME into small m by RE square. This is the expression for force. Okay, right. Now, the acceleration experienced by the mass m, the acceleration experienced by the mass m, which is usually denoted by the symbol small g. So actually we are using small a to represent acceleration, to represent acceleration. Okay, right. But here when you are talking about acceleration due to the gravity, acceleration due to the gravity of earth, we are using a small g to represent acceleration by the earth. Okay, why? Because there should be difference, no, there should be difference. So here in this class we are in a discussion about the acceleration experienced by the body due to the earth's gravitational force. Okay, due to the force experienced by the earth naturally, right? That is what gravitational force. That's why here we are using small g to represent acceleration experienced by the mass small m. Okay, right. Now, from Newton's second law of motion, this is what you know very well. F is equal to mg. F is equal to mg. From this I can write g is equal to f by m. No, when I am writing g is equal to f by m, when I am writing g is equal to f by m, that is equal to g into me by re square. G into me by re square, because m will get cancelled, no. So small g is equal to capital G into capital me by re square. This is what the expression for acceleration due to gravity of earth. Acceleration due to gravity of earth. Okay, right. And here itself, this acceleration is readily measurable. So this value you can measure. In this entire universe we have 8 planets and we have stars, right? And comets, meteorites, right? Asteroids. So every celestial body or any celestial body has its own mass, right? So that's why you can calculate gravitational force, which is because of sun on its surface, and which is because of earth on its surface or on its surroundings, or because of Jupiter, because of Mars, right? That's why what is the conclusion means here, the small thing is about g. G is readily measurable. G is readily measurable, and this is the formula. For example, if you want to calculate acceleration due to gravity, due to the acceleration due to earth, acceleration due to earth, here we have to take mass of earth, already written here, E means earth, and we have to take radius of earth. And this value, I think mass of earth is 6 into 10 to the power of 24 kg, and radius of earth is 6400 kilometer, and G value is 6.67 into 10 to the power of minus 11 Newton meter square per kg square. By writing all these values, you can calculate, and you can calculate mathematically, you can calculate small g value, and generally you are getting that is 9.8 meter per second square on surface of earth. Okay, right. And this is what the measurement of this value I already told you just now, just before 1 minute I told you, that is 6.67 into 10 to the power of minus 11 Newton meter square per kg square. This is what, how that value we got, that we discussed in our previous class, right? In our previous class, where the gravitational constant, our previous class is gravitational constant. So there by Cavendish experiment, the great scientist, by Cavendish experiments, we calculated, and how I explained you how we calculated G value as 6.67 into 10 to the power of minus 11 Newton meter square per kg square. Okay, right. And with the combined knowledge of small g and RE enables one to estimate ME also. So what he is saying is, if you know these three things, you can calculate this one. Otherwise, if you have an idea about this one, and this one, then you can estimate mass of earth, that is like already I told you, 6 into 10 to the power of 24 kg. Okay, that's why there is a popular statement, that is what Cavendish weighed the earth. Cavendish weighed the earth. Okay, right, that is. And one more thing I am saying, so whatever the G value I told you, that is 9.8 meter per second square, which is not a constant value, which is changing from place to place on surface of earth, and which is also changes when you are moving away from surface of earth, and when you are going deep inside the earth also small g value changes, which is not constant. So in our next class, that is only our topic, that is what variation of acceleration due to gravity, right? So in our next class we will concentrate on acceleration due to gravity below and above the surface of earth, below and above the surface of earth. Okay, right, thank you.